So the big question, why in the world do we care about all of this? Because internal forces connect the objects of a system together, but cannot change the motion of a system. Okay, so all of the forces inside of the body can't change the motion of the body. As the heart pushes out when it beats, it's not causing me to move faster. External forces could be balanced by other external forces. So a balanced external force, which we know cannot change the motion of a system. If I begin to push on my face this way, and then I begin to push on my face this way, and then I do it at the same time, it's now balanced. And remember, if you have balanced forces, one going this way, one going that way, you're moving with a constant velocity. Could be at rest, or you could be moving with a constant velocity. So it's the same thing with an external force. So, which is going to bring me back to Newton's first law. I see a lot of students try to tell me that an object in motion will stay in motion unless acted on by an outside force. No. No. The problem with that is there may be many outside forces outside of the system. There may be many external forces, and they could balance each other out. If they are unbalanced, that will change the motion. So that's why back when we went through Newton's first law in Unit 1, we were so specific about talking about unbalanced forces. Here's Newton's second law as it applies to an object, which we already know. This is a review. The stuff that makes it go minus the stuff that holds it back equals the mass's object times the object's acceleration, right? Here's Newton's second law as it applies to a system. The unbalanced external forces on the system in the same direction as acceleration minus the unbalanced external forces on the system opposite the direction of acceleration. The stuff that makes it go minus the stuff that holds it back equals mass times acceleration of the system. All right, so now we're going to look at some examples. A set of carts. The first one is a horizontal train. Set of carts A, B, and C with frictionless bearings are connected by ropes 1, 2, and 3. 1, 2, 3. Rope 3 is being pulled, so it has a tension of 30 newtons. Calculate the acceleration of the carts and the tensions in the ropes 1 and 2. Maybe you've seen a toy like this where you pull one rope and it's got other carts connected to it, and then they all kind of move with the same speed. Hopefully you noticed that. If not, let's take a look at it. Here's a free body diagram for cart A and Newton's second law equation. So cart A, vertical forces cancel out. All that's left is the tension in 1. Tension in 1, stuff that makes it go, minus stuff holding it back, nothing holding it back, equals mass times acceleration. For B, we got a little bit more going on. We have tension going left, and then we have tension going right. So the stuff that makes it go is going to be the bigger tension, minus the stuff holding it back is going to be Ft1, equals mass times acceleration. For the third one, we have tension 3 making it go, tension 2 holding it back. So the stuff that makes it go minus stuff that holds it back equals mass times acceleration. Free body diagram for the A and B system. If we were to only treat A and B as a system, well, now we don't have anything holding it back. So all we're looking at is the tension 2. So the stuff that makes it go is going to be the combined mass of the entire system, times the acceleration of the entire system. For BC, same thing. But with this, we do have tension 1 holding back the system. You see the dotted lines? It's often pretty useful to draw in these dotted lines for when defining your system, especially if you're taking little pieces of a larger thing. Put little dots around it. That way you know what you're dealing with. I think the dots help to see, specifically here, that tension 1 is pulling on the system. Tension 3 is external to the system, so it's pulling on the entire system. And again, stuff that makes it go minus stuff that holds it back equals combined mass. free body for the whole thing. Tension 3 is what makes the entire system go. And then we're combining all of our masses and the acceleration of the entire system. So if I were looking for tension 3 alone, I would start here. Look at the entire system. Meanwhile, if I just needed to find out what tension 1 was, if I've already found tension 3, then I would use this equation. Right? Anything that's going to allow me to solve for tension 1. You could even go backwards all the way to the first equation. There we go. This problem can be easy or difficult depending on which system we choose to consider for each part of the problem. To find the acceleration, we'll look at the entire train because the whole train is moving as a system. It's all accelerating at the same time. So we have tension 3 equals our combined mass times the acceleration of the system. Now we know that Ft3 and all three masses, so plugging in, we know Ft3 is 30. Plug those in, and we get acceleration of 2 meters per second squared. To find Ft1, it would be easiest if we only considered cart A, because that's the only force acting. So it's going to be stuff that makes it go minus nothing equals mass times acceleration. And now we have that tension. To find Ft2, AB system. So let me go back and give you the AB system, because it feels like it's been forever. No. AB, here we go. So AB system, Ft2 equals mass A times mass B. Okay. There is nothing pulling on the system in the leftward direction. So the only force acting on the entire system is Ft2. And that's why it's useful to use AB system. So here it is. Ft2 equals ma plus mb times acceleration. The acceleration, notice that it's the same acceleration that we found to begin with because everything within that system is accelerating at the same rate. Your heart is moving along the 100-meter dash at the same rate as your lungs, right? Everything within the system is moving at the same speed. Ft2 equals 24 newtons. What did we just see? To solve for the acceleration of objects in the system, we did a Newton's second law equation for the entire system. But first, whenever we have forces, we have to first draw a free body diagram. From the free body diagram, that's how we're creating this Newton's second law equation. Okay? To solve for the forces internal to the system, we need to choose a subsystem where the force we want is external to the subsystem. Tension 1 was internal to the whole train system, but external to cart A. Tension 2 was internal to the whole train system, but it was external to the AB system. Vertical train, coming up next.